Hi, so this is second half of lecture 18. And in the second half, what we will do is we will continue looking at the motion that combines rotation and translation. And we will do so by looking at more specific examples. I want to start with the example of a car. This is slide number 6. Let's say you have a car. This car has 4 wheels. And let's say this car is moving with some velocity, v. Then, as this car is moving with some velocity v, it has energy. And there are 2 types of energy here, basically. So first of all, you have the car itself. This car has kinetic energy mv²/2. And then you have 4 wheels. Let's say wheels have mass m. Then all 4 wheels will have kinetic energy mv²/2. So you will have 4 times mv²/2. And the wheels, of course, move with the same velocity as the rest of the car's body. But that's not the whole story. That's not the whole energy. We have also rotation. These wheels, they rotate. And because they rotate, they have additional rotational energy, which is, again, 4 times I times ω² divided by 2. And now the question is what fraction of car's energy is in the rotating wheels? So what's the fraction of this energy compared to the whole energy? So one thing that I want you to think about is, let's say if we had exactly the car that was very similar, it had same mass, but if it had larger wheels, again, same mass, but larger in radius. Think about whether this car with larger wheels will have more energy in the rotation of the wheels, or this car with smaller wheels. So why don't you think about that, pause the video, and then we will run through math and we will see how this works. Okay, so the question was, what fraction of energy is in the wheels, and does this fraction change if I go to, how does this fraction change if I go to larger wheels? So let's see, let's look at this thing over here. This is rotational energy. Let's start with the moment of inertia. Now wheels, they have complicated structure, but for simplicity, let's assume that all of their mass is in the rim out here. This is of course not true, but let's make this approximation. And then what we have, the geometric shape of the wheel is kind of a circular loop with radius r. And if I have a loop, then I can look up moment of inertia of a loop. And the table of moments of inertia tells me that if I have a loop, its moment of inertia is mass times radius squared. Okay. Now let's think about angular velocity. My angular velocity, I know, since there is no slipping, I know that my angular velocity is my translational velocity divided by r. So now I will use these 2 and I will plug them in here. My rotational energy will turn out to be 4 times mr² times v²/r² divided by 2. This r² conveniently cancels out with that r², and I end up with twice mv². So this is a very interesting example. So it turns out that when my wheels rotate, if you look at this, their translational energy is also 2 times mv squared. So it looks like they have the energy is equally distributed between translational motion and rotational motion. It's exactly 50-50. And it also looks like there is no radius here. There is no radius here. So it looks like it doesn't really matter whether my wheels are big or if they are small. So why is that? To understand why that's the case, we have to look back at these formulas and see how the radius affects different things. So if you look at the moment of inertia itself, you will see that the moment of inertia goes up when you have bigger wheels. So if you have something big, then this thing is more difficult to rotate. And you know, then you would expect a lot of energy to go into those wheels. But there is this interesting coincidence here. The coincidence is that if you have large wheels, then they rotate slower. Okay, so if you have a small wheel and if you have a large wheel, and if they move with the same velocity, you can think about this, pause and think about it. As they move 1 meter, if they both move 1 meter, this wheel will go to more rotations and that big wheel will go to less rotations. So big wheels have lower angular velocity. And that's why, even though they are more difficult to rotate, you can move fast, basically, without them really rotating fast. And those two effects tend to cancel out perfectly. And in the end, we get this result that it doesn't really matter what size wheels you have. They take exactly the same fraction of energy, which is if this approximation of a loop is correct, then you know, that's about 50% of the energy of the total energy of the wheel. So now we talked about energy. Before we move to next examples where energy will play a very important role, I just want to remind you how energy conservation works. So the way energy conservation works is that if there are no non-conservative forces, if all the forces that you have are conservative forces, then energy is conserved. And whatever your energy is in the beginning, whatever happens, you will have the same energy in the end. Now, this beginning and the end, it's completely up to you how you define your beginning and how you define your end. It's usually problem dependent, so whatever suits you. And we, in this introductory class, we won't look at complicated types of energies. Basically, we only look at kinetic energy, energy of the motion, which is mv squared over 2. And we will sometimes also have mgh when things move up and down in gravity. And sometimes we will have springs. So that's k delta x squared over 2. And now we know that when things rotate, we have to add this I omega squared over 2. So you know, there could be other types of energy, but in our homework problems, this is what you have. And then sometimes some of these energies will be absent. If your spring is not stretched, or if there is no spring, then you're not going to have this. If your object isn't moving, you're not going to have this. You will have different combinations of those, but there are some who will always be conserved. Okay, so now that we remember this, let's look at another example. And this is an example of a loop-a-loop. What's happening here is that you have this loop, which is to a high degree circular. It has a radius of r. And there is an object here. This object will slide down or roll down. And the question is, will this object make a loop? So you probably remember we had a homework problem on this, and we ran our, I think we had also a demo about this. So your first guess may be that you have to start this object from here, but then turns out that that's not enough. In fact, for you to make the loop, you should start your object much, by some amount higher. So what I want to look now is I want to look at how this result changes if instead of a box that slides down, you have a solid sphere that rolls down, or a loop that rolls down. So what kind of difference does rolling make? Just to remind you how this worked for the case of a particle that didn't roll, if we had something like a box that simply slid down, basically what's happening here is that as you attempt to make a loop, you want to make it all the way to the top. And when you are on the top, since this is a circle and since you want to continue moving on a circle, at this point, your acceleration is v squared over r. So you need to have a force. Force is mass times acceleration. So m v squared over r has to be equal to your force. And in this case, the force is the force of gravity. Now, what happens if you end up at this point and you have higher velocity? If you have higher velocity, then gravity isn't enough to keep you on this loop. So normal force will kick in. There will be some extra normal force here. And the normal force will help you to keep this object, which is in this case just a box, to keep this object on the loop. But if your velocity is lower than this, then there will be no normal force. And if velocity is low, then there will be too much force, and this force will kind of loop you like this. So it will detach you from the loop itself. And so this threshold, when you just barely make the loop, is when you have exactly this much velocity. So mass cancels out here. If your velocity is the square root of g times r, where r is the radius of the loop, then that's the amount of velocity that you must have, this or more to make the loop. Otherwise, you will fall short. Now, if I need this much velocity, then the question is, here, how high should I start? And to answer this question, what we do is, so let's say this is h. What we do is we simply invoke conservation of energy. So we say, in the beginning, when I start, I have mgh amount of energy. And then this energy, by the time I'm here, this energy, now I have, what do I have? Now I have mg times twice r amount of potential energy, once r, twice r. And plus I have some kinetic energy mv squared over 2. So if h is high, then my velocity will be high. And to find the h that I need, what I do is, okay, first of all, I will cancel out my mass. So my h will turn out to be twice r plus v squared over twice g. I'm simply dividing by g here. And if I plug in this expression for v, I will get twice r plus g times r divided by 2g. G will cancel out, and this is equal to 2 plus 1 over 2. This is 5/2 of r. Okay, so this is how high I need to be. I need to be 5 halves of R. This is 2.5 R, so 2 R and then half R. And then I will have, ignoring friction, I will have enough energy so that by the time I get here, I have sufficient velocity. So this is a very interesting example. Yeah, this is a very interesting example. It shows you that basically the mass doesn't matter. It doesn't matter how heavy this object is. G doesn't matter. So this result holds for Earth and Moon and Jupiter, no matter where you are. It's always 5 halves of R. Now what I will do is I will solve exactly the same problem for a solid ball, solid spherical ball. And I want you to pause and I want you to think about whether I will need to release this ball from higher or from lower than what I needed for the box. Okay, so let's do that. I will not erase this result because I want to keep it. Let's write that this is for a box so that we don't forget. So let's see what happens when I have a sphere. When I have a sphere, I will write down conservation of energy again. My initial energy is still mgh, although this h may be a different h. And by the time I'm here, I have potential energy of mg twice r plus kinetic energy of mv squared over 2. So everything is pretty much similar to the box, except now my solid ball a spherical ball is rotating. So some energy goes into rotating it. And this energy is I omega squared over 2. So again, I for the sphere is, what's I for the sphere? I have to look it up. I'm looking into the table, and the table tells me that sphere has I of, a solid sphere has I of 2/5 of mass times radius squared. This radius is now the radius of the sphere. So don't confuse it with the radius of the loop. Okay, so if I plug that in here, I will have 2/5 of mass times r squared times omega squared. And this r squared times omega squared will turn into velocity squared. So that's 2/5 of mass times velocity squared. So this happens pretty often. You have I omega squared, but then there is a factor of r squared in here, a factor of r squared in here. So you, in the end, usually end up with mv squared with some number in front. Okay, so 2/5 of mv squared over 2. And now if I solve for h, again, mass will cancel out. Instead of v, I will plug in this result, and I will get my h to be equal to, I will divide by g, so that's twice r plus half of r plus 1/5 of r. This is, what's this? So half plus 1/5 is 7/10, 2.7 r. Okay. 2 plus 7/10, 2.7 r. This is for the sphere. And this is, let's rewrite this as a decimal as well. So this is easier to compare. This is 2.5 r. So you see, if I have a sphere, I have to start from higher up, which is not surprising because some amount of my energy will be lost to rolling the sphere. Now, if you had to do this for a cylinder, for a hollow sphere, or any other object, all you would have to do is you would have to plug in the appropriate expression for the momentum, for the moment of inertia. And the way it will work out is that if you have an object that's more difficult to rotate, then it will take away more energy. You will fall short of your velocity goal here, and therefore you will have to start from higher up. So, for example, if you have a hollow sphere instead of a solid sphere, then the moment of inertia of hollow sphere is higher because you have more mass further away. Hollow sphere is 2/3, yeah, 2/3 of mr squared, and for the hollow sphere you will get 2r plus half of r plus 1/3 of r. This will be 5/6. What is 5/6? 2 and 5/6 of r. Well, this is more than that. So for the hollow sphere, you will need to start it even higher. And in your homework problems, you will have a bunch of problems where something rolls. I think in one of the problems you have a roof, and something rolls off the roof, and then it continues falling. And so the basic idea is that in the beginning you have this rolling, and then you have a projectile motion. So you have to find your velocity just before this object leaves the roof. And to find that velocity, you will use conservation of energy. Your mgh will go into velocity, but some part of it will be lost to rotations. So you do exactly the same thing, basically. You write that your mgh in the beginning is equal to whatever the energy is in the end, and one piece in here will be rotational energy. So hopefully this is enough to tell you which way, how to start solving those problems. And if you cannot completely figure it out, please join our Zoom help room on Wednesday and Friday at between 12:30 and 2:30. So this is all for now that I wanted to tell you about rolling. And I want to finish this lesson with a little bit of a slightly different topic that will be useful next week. And this is the topic of torque. This is now slide 9 on my lecture slides. So just to remind you, if you have something that you want to rotate, let's say I have this circle that's fixed, and I want to rotate it counterclockwise, then I have to apply a torque. Torque is force times distance times sine of the angle. So this sine and this distance are important. If I apply my force here, then I will have no torque. And if I apply my force at a 0 angle, again, I will have no torque. So this is not going to work. This is not going to work. The most optimal angle is 90 degrees. That gives me sine equal to 1, which is the most I can get out of a sine. And what I want to do now is basically this formula holds, but I want us to get familiar with a different formalism, the formalism of a vector product. And it may not be obvious now why this is necessary or useful, but this will be necessary and useful. And there are many problems where it's much easier to use the vector product because it's not as simple to figure out what the angles are exactly. So basically the vector product, just to remind you, when you multiply two vectors, let's say I want to multiply my vector r and my vector f, and then torque will be a vector which is a vector product of my r and my f. What I do is, if I'm given my r and my f in components, x, y, and z components, and I can write my R as its X component times I plus its Y component times J plus its Z component times K. And similarly, I can write out my force as the X component of my force times I plus Y component of my force times J times Z component of my force times K. And depending on which way my force and my R point, these numbers will be different numbers. And so if I want to take a vector product now, all I have to do is I have to multiply these two, and I will multiply numbers as I do usually. So these numbers I will just multiply as regular numbers, but the symbols I, J, and K, I will multiply using this multiplication table. I times I is 0, J times J is 0, K times K is 0. So basically every time I multiply something by itself, it's 0. If it's a vector product, then I times J is K. J times K is I. But if I invert this, then J times I will be equal to negative K. And there are these rules that this multiplication table is on slide number 10. But there is a certain pattern there that you will, if you do it once or twice, you will catch the pattern very easily. There are other ways of doing this. You could put those things in a matrix. There is a matrix formalism, but you can look it up on YouTube if you want. But it's basically exactly the same thing. Okay, so maybe if this is too abstract, I thought it would maybe helpful to you if I go to a specific example. So let's say I have my R vector, which has X, Y, and Z components. I'm just making up numbers 2, 3, and negative 5. And let's say I have a force, and let's say this force has components 1, negative 2, and 1. So X component is 1, Y component is negative 2, Z component is 1. I want to vector product these two. So how do I do R times F? So if you are good at this from calculus, then feel free to skip. This is the last thing that we will do in this lecture. But if you want to stick around, what I will do is I will multiply these things. So I take twice I plus 3 times J minus 5 times K, and I multiply it by once I minus twice J plus once K. So let's carry out the multiplication. It's twice I times once I plus 3 times J times once I minus 5 times K times once I minus 2 times I times, where am I? Once, so what am I doing? Sorry. So I did this times that, this times that, this times that. I will have 9 terms in total. So let me take this and multiply it by all 3. So I will have 3 times J times 1 times I minus 3 times J times 2 times J plus 3 times J times 1 times K. And now I will take this and I will multiply all 3. So minus 5 times K times 1 times I plus 5 times K times 2 times J minus 5 times K times 1 times K. Okay. So now I will look at the multiplication table. So first of all, I know that when I multiply I by I, j by j, k by k, I get zeros. So these terms immediately go away. So 3j times 1's I, that's 3 times j times I is negative k. So negative 3 times k. Now 5k, negative 5k times 1i, k times I is j. So this is negative 5 times j. So number gets multiplied by a number as usual. And for ij case, I will use the multiplication. That's the idea. Now plus 3j times 1's I, j times I is negative k. So this is negative 3 times k. 3j times 1's k, j times k is I, so this is 3 times I. Okay, negative 5k 1's I, k times I is j, so this is negative 5 times j. Good. And the final term, 5k times twice j, k times j is negative I, so this gives me negative 10 times I. And now what I will do is, since I'm done with all the multiplications, I will combine k with k, I with I, j with j, and I will get, starting with I, 3 minus 10, negative 7i. Where is j? Negative 5j, negative 5j, negative 10 times j, negative 3k, negative 3k, negative 6 times k. Okay, so this is my final result. I multiplied these two vectors with using a vector product, and I got this vector. I got a vector that has x component equal to negative 7, y component equal to negative 10, z component equal to negative 6. So if I have this force and if it's applied at this position, then my torque is, this vector. It's a bit boring, but I hope it's straightforward. There are just the simple algorithmic rules that you have to follow. So I want to stop here. Why we do this vector product will become clear later next week. And again, the Zoom help room is on every Monday, Wednesday, Friday. So if you have any questions about this or homework or studio, please join. Thank you.